This visualizes what happens the moment you hit compile. That clean, organized C code shatters into a dense waterfall of raw hex codes. C code is purely a human abstraction. The physical processor never interacts with those readable lines of text. Instead, a compiler acts as a literal translation engine, converting your abstract syntax into sequences of bytes called opcodes. These opcodes dictate exact mechanical hardware operations on an x86 or x64 architecture. Modern compilers will even rewrite your logic behind the scenes. If you write a printf statement with no formatting variables, the compiler secretly swaps it out for a leaner puts function to optimize execution. These high-level abstractions hide the physical execution logic and structural vulnerabilities from the developer. To optimize performance, reverse engineer a program, or execute a binary exploit, you have to strip away those abstractions entirely. You must discard the software mental model and rebuild your understanding of code execution from the physical silicon up. This animated model shows a CPU die, zooming into a single 64-bit storage block called racks. These CPU registers are the apex of the memory hierarchy, ultra-fast, zero-latency physical hardware containers sitting directly on the processor. To maintain backward compatibility with older x86 systems, these 64-bit registers are not treated as single indivisible buckets. They use a nesting doll layout. You can address the lower 32-bit segment completely independently as EAX. The compiler maps specific C data types directly to these nested layers, allocating a 2-byte integer to the 16-bit AX segment or a single character to the 8-bit AL layer. The core operation for interacting with these hardware layers is the move instruction. It picks up a standard numerical value and drops it directly into one of these containers. At this stage, a register is just a generic value bucket. It only changes behavior when the instruction syntax forces it to act as a memory pointer. That happens when you introduce the dereference bracket operator. Placing brackets around a register instructs the CPU to stop treating the number inside as a standard value, and instead use it to look inside an external RAM address. This brings us to the LEA, or Load Effective Address instruction, a distinct mechanical operation from MOV. Unlike MOV, LEA completely ignores what is stored in RAM. It hijacks the CPU's memory addressing hardware to perform rapid arithmetic, calculate a target address, and store that raw address inside a register. Variables do not exist here. There are only generic silicon containers, and their entire function is dictated by surgical instruction syntax. This diagram maps out the external system RAM, specifically the stack, which grows strictly downward as memory is allocated. This is where the processor goes when it runs out of space on the die. When a program passes data to a function, it follows a strict rulebook called the System V AMD64 Application Binary Interface, or ABI. The primary rule of the ABI is that the first 6 function arguments bypass memory entirely. They are loaded directly into designated hardware registers like RDI and RSI. But any argument beyond the 6th triggers an overflow mechanism. That extra data is pushed downward, falling past the CPU directly into the stack. The moment that function executes, it builds a stack frame, a physical, temporary, local environment constructed entirely in RAM. In this focused view of the RAM column, we see the function prologue in action.
The base pointer, or RBP, drops an anchor onto a specific memory address, creating a solid boundary line for this new environment. Next, the stack pointer carves out the required space. It slides downward, subtracting exact byte values to allocate room for local variables. By deconstructing a compiler instruction like move dword ptr rbp-4, we can forensically locate a local variable in memory. The target is a negative offset from RBP. This proves the variable is local because it lives physically underneath the base pointer's anchored boundary. High-level local scope is an illusion. It is merely a rigorously maintained physical boundary of pointers sliding up and down in RAM. If a CPU only executes math and moves data from place to place, how does it evaluate complex conditional logic? This diagram illustrates the rflags register. You have to abandon the idea of a register as a standard data container. This is a row of 64 independent binary on-off switches. Think of rflags as the CPU's hardwired status dashboard. It reacts instantly to the outcome of arithmetic instructions. Take a comparison instruction like CMP. When it executes, it performs a silent subtraction on two values without actually saving the numeric result. If that subtraction results in a perfect 0, the CPU physically flips the 6th bit on the dashboard, the 0 flag, to an active state. Negative outcomes trigger different switches. If the subtraction yields a negative number, the sign flag at pit position 7 flips on instead. Control flow does not evaluate variables. Program branching is a blind mechanical reaction to these specific dashboard lights. Branch instructions like JE, jump if equal, or JZ, jump if 0, are simple triggers that read the hardware dashboard. If the JZ instruction sees an active 0 flag, it intercepts the instruction pointer and violently redirects the path of code execution. Software logic is a myth. Program flow is strictly dictated by physical state changes reacting to raw mathematics. This composite view brings all three architectural pillars into a single execution state: the CPU registers on the top left, the downward growing RAM stack on the right, and the R flag switches on the bottom left. Compiled code manages rapid data in the registers, anchors state boundaries in the stack, and steers execution flow using physical flags. Consider an exploitation scenario where an attacker feeds an oversized string of input data into a vulnerable function. The sheer volume of data exhausts the ABI's 6-register limit, pushing the overflow directly into RAM and rapidly flooding the local space inside the stack frame. Because the CPU executes instructions blindly, the overflow violently breaches the RBP local boundary. The consequence is total control. The attacker intentionally overwrites the function's return address, hijacking the instruction pointer the moment the function finishes. Alternatively, an attacker can corrupt local memory enough to trick an instruction into flipping a hardware flag, triggering a jump that grants false administrative access. The ultimate truth is that the processor has no concept of malicious behavior. It flawlessly executes whatever is physically loaded into memory and the registers. High-level software logic cannot protect a program if the underlying physical architecture is manipulated. To master reverse engineering or binary exploitation, you must stop reading the software illusion and start speaking the exact literal language of the hardware.